Welcome to a screencast on measurement and significant figures. One thing that scientists do quite a bit of is measure things, and we need to make very careful measurements when we're doing this. Let's start with a simple example. How far does Stephanie's student travel to get to school? Now, maybe let's change that to a slightly more realistic picture of students going to school. And of course, depending on the student, they might go a different distance. And let's say for purposes of this example that Stephanie's student travels 4 miles to get to school. Now note that this is an example of what's called a physical quantity, and physical quantities are described by both a number, in this case 4, and a unit, in this case miles. Both of those are needed in a measurement, both the value, the number, and the unit that you are using. Now, scientists, chemists in particular in this case, are typically going to use SI, or Système International de Unité, or metric units for our physical quantities. So we're going to use things like meters for length and kilograms for mass. The basic temperature unit is Kelvin. Time, we use seconds as the fundamental unit. Amount of substance will be in moles. Electric current is in amperes. And luminous intensity, kind of a not very commonly used value for chemists at least, is in candela. And of course we will use variations on this, like centimeters, not just meters, and grams, not just kilograms, and degrees Celsius rather than just Kelvin, etc. But these are the fundamental or basic units we'll be dealing with. Now, it's also worth noting that we use some prefixes to deal with common multiples of these units, and you should get familiar with these. For example, mega is 1 million, or 10 to the 6th. And kilo is 1,000, or 10 to the 3rd. And deci is a tenth, 10 to the minus 1. Centi is 1/100th, 10 to the minus 2. Milli, 1,000th, 10 to the minus 3. Micro, 1/1,000,000th, 10 to the minus 6th. And nano, 1/1000,000th, 10 to the minus 9. There are, of course, other prefixes as well you may have heard of, like giga, for example. But these are the probably 7 that you're going to use most commonly, and you should definitely make sure you know these values, or these what these prefixes stand for. Now, when we do measurements, we might measure something like the volume of the Earth's oceans, which is a really, really big number. It's approximately 1,3 followed by 20 zeros. Now, this is a really big number. It takes a long time to write out all of those zeros. And so we often, of course, use a shorthand version of this called scientific notation. And instead of writing 1,3 followed by 20 zeros, we can write 1.3 times 10 to the 21st liters, of course, for make sure we have the units in there. Now, note when we do scientific notation, we're always going to have a number here that's 1 or bigger, but less than 10, and then times 10 to the appropriate power. And of course, we can use scientific notation for very, very small values, like the diameter of a hydrogen atom is about 0.0000000000074 meters. And in scientific notation, this would be 7.4 times 10 to the negative 11th. We write the number between 1 and 10, 7.4, and then to the appropriate power. And note 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 powers of 10 is how much we have to go to get to a number between 1 and 10 at the start. And similar idea here, of course, if you start at the 1.3, you're going to count over 21 powers of 10 to make that conversion. Okay, now let's move on to measuring some actual values, like how we might do this. So suppose we have a candy bar. What's the mass of the candy bar, and how would we determine it? And of course you'd say, well, get out your scale, get out your balance, put the candy bar on the balance, and in this case we have a triple beam balance, kind of old school, and you move the weights here to make the triple beam balance actually balance, and then read off of that. Most likely you, however, in lab will be just simply using an electronic balance where you zero the balance first, you put the thing you're going to weigh, in this case the candy bar, on the balance pan, and then a reading is just simply given to you, in this case 104.987 grams. Important to note, if your balance reads to the thousandth place, so 0.987, you want to record that whole value because all of that has been measured. Now, what if we're measuring the length of something, for instance, like the paper clip shown here? Well, you'd probably say, let's put a ruler next to the paper clip, put the end, the zero of the ruler at one end of the paper clip, and then we're going to estimate where the other end of the paper clip falls on the ruler. And notice we're definitely more than 1 centimeter and less than 2. And in fact, we are 1, 2, 3, more than 3/10, but less than 4/10 of a centimeter. And if you look at where the end of the paper clip is, you might say you're maybe, I would say, 7/10 of the way or so from the 0.3 to the 0.4. And so we might then estimate the length of the paper clip to be 1.37 centimeters. Now, of course, somebody else might say it's about 8/10 of the way or maybe 6/10 of the way. There's a little uncertainty or variability in that last digit, which is estimated. And every experimental measurement is going to have some degree of uncertainty. And that's going to depend upon both the measuring device we use and how good you are at using that device. So measure length with a ruler, we're estimating in the case of the paper clip to the hundredths place. If we're measuring the volume in a graduated cylinder, here we're maybe going to estimate that it's between the 21 and the 22, maybe about 6/10 of the way or so. And so here we're estimating to the 10th place because the graduated cylinder has markings for every milliliter, and we're estimating to the 10th of a milliliter. And the uncertainty in a measurement is going to be expressed by what are called significant figures, the number of significant figures in that measurement. The measurement of the volume using this graduated cylinder has 3 significant figures, and it's known to the tenths of a milliliter. The length of the paper clip had also 3 significant figures, but it was known to the hundredth of a centimeter. That was our approximation. And every time we do a measurement, then every digit in the measurement is what's called a significant figure. And the last known digit, which is going to have some degree of uncertainty, is the last significant figure. And in the case here again of the paper clip, there are 3 significant figures, and our last significant figure is to the hundredths. So significant figures tell us something about how good our measurement is. So a little bit of practice. How many significant figures are there in each of the following measurements? And think about it before I tell you the answer. And of course 17.4 has 3 significant figures. The 1, the 7, and the 4 all are significant. How about 230.8? And hopefully you say the 2 is significant, the 3 is significant, so is the 0, it's the result of a measurement, and the 8, that's 4 significant figures. And whenever we have an internal 0, that's an actual measured number. It's not 1, it's not 9, it's 0. So that counts as a SigFig. Alrighty, 0.00045 has how many SigFigs? And if you said 2, you are right. These leading zeros, all of these are just placeholders. we don't have an actual measured value till we hit the 4. So the 4 and the 5 are SigFigs, two significant figures. And one way to think about this is if we wrote this in scientific notation, this would be 4.5 times 10 to the minus 4th, and then all of those leading zeros would essentially disappear because they're just placeholders. They're not actual results of measurements. And last, how many SigFigs in 160.70 pounds? And if you said 5, you are right. The 1, the 6, the internal 0, and the 7 are clearly all SigFigs. And then this last 0 is the result of a measurement. It's a trailing 0, not a leading 0. And if it wasn't the result of a measurement, if our scale didn't read to the hundredths of a pound, we just wouldn't write this. We'd write 160.7. So trailing zeros are going to be significant figures because they are going to be results of measurements. And that's it for this screencast on measurement and significant figures.